Hello students, good morning. Welcome to the online class, Standard 12, Subject Chemistry. Students, in the 12th Standard Chemistry, we have been discussing unit number 6, Solid State. And in that solid state lesson, the concept which we are going to discuss today is packing in crystals. We are going to learn how the constituent particles like the atoms, molecules or ions in a crystal, how they are arranged, the manner in which they are held together. That will be discussed under the heading packing in crystals. Is it clear? So what is the concept of today's video lesson? Packing in crystals. Okay, look here students. Here I have taken a picture of the arrangement of fruits in a fruit shop. Have you ever seen this? Yes, you might have seen. Okay, here the fruits are arranged very tightly or very close to each other. Why? If they are not arranged tightly, they can occupy more space. So more space is required to arrange the quantity of fruits, isn't it? Yes. Okay, so what is the reason for arranging them very closely? To avoid the free space occupied by the free space left between the fruits. Okay, likewise in the crystalline solid also the packing will be very tight. Okay, the reason is given here to maximize the attractive force between the constituent particles. When the constituent particles are as close as possible, the attractive force between them will be large. Okay, so in order to maximize the attractive force between the constituent particles, they are packed together as close as possible. Also we can say in order to minimize the free space left over. Because of these two reasons, the particles are very tightly packed together in the case of a crystalline solid. Okay, so what is given here? To maximize the attractive force between the constituent particles, the particles are held together, or we can say they are packed together as close as possible. Okay, now let us see the various types of arrangements of particles. The first type we are going to see is linear arrangement, or it can be called as the arrangement of constituent particles in one direction. Okay, we can say one dimensional arrangement, 1D arrangement. Okay, what is 1D arrangement? The constituent particles like atoms will be arranged only in one direction as shown in the figure. Look at this figure. These are the constituent particles. Each sphere is an atom. Each sphere is an atom. Okay, and the atoms are arranged only in one dimensional, only in a linear fashion. And so this arrangement is called as linear arrangement of spheres. Here the term spheres can be used instead of atoms, molecules or ions, or simply we can say the constituent particles. Okay, so what is linear arrangement of spheres in one direction? In a specific direction, there is only one possibility to arrange the spheres in one direction, and it is called as linear arrangement of spheres in one direction. And dear students, for every arrangement we have to calculate the coordination number. What is called as coordination number? Do you know? Coordination number is nothing but the number of neighboring atoms for a particular atom, and the coordination number will be same for all the atoms in an arrangement. Okay, so the number of neighboring atoms for an atom will be equal to its coordination number. Here look at this pink color atom. It has how many neighboring atoms? It has 2 neighboring atoms. One is in the right side and the one more is in the left side. So here what is the coordination number? The coordination number is 2. So in the case of linear arrangement of particles in one direction, the coordination number is 2. Okay, then let us see the second type of packing, which is called as two-dimensional close packing. Two-dimensional close packing is not a new one. Just now we have seen about one-dimensional arrangement. No, when that one-dimensional arrangement is repeated in a two-dimensional way, it is called as two-dimensional close packing. Okay, when this row of arrangement is repeated, then we will get the two-dimensional close packing. And here there are two types of two-dimensional packing. Those are AAA type packing, and the one more is ABAB type packing. Okay, so what are the types of two-dimensional close packing? There are two types we have. One is called as AAA type packing, and the one more is called as ABAB type packing. Let us see about them one by one. Look here, ma. First, let us see about AAA type. Okay, va? Okay. Look at this picture now. This is the picture which shows the two-dimensional close packing of AAA type. Okay, why it is called as AAA type? Look here, this first row of atoms, it is similar to the one-dimensional arrangement, isn't it? Yes. Now we can name this layer as A. The first layer of this arrangement can be named as A. Now this second row is placing behind the first row. The second row of atoms is placed behind the first row of atoms, and here in both the rows the atoms exactly fit each other. Okay, so this second row can also be called as A type arrangement. So when the A type arrangement is repeated, it is called as AAA type arrangement. Okay, we can say that the linear arrangement of spheres in one direction is repeated in two dimension. The simplest one-dimensional arrangement of atoms is repeated in two dimension to give the AA type two-dimensional packing. Okay, and in this case all the spheres of different rows align vertically as well as horizontally. They exactly fit which each other. Okay, okay, and here we have to calculate the coordination number. What is coordination number? The number of neighboring atoms for an atom is called as coordination number. Look here, look at this atom. If we consider this atom, it is surrounded by how many other atoms? It is surrounded by 4 other atoms. It is given like this. Likewise, if we take any atom in this AA type packing, it will be surrounded by four other spheres, and also here the coordination number is 4. Okay, here what is given? The linear arrangement of spheres in one dimension is repeated in two dimension to give the AA type packing. Here each sphere is in contact with 4 neighbors, and hence here the coordination number is 4. Okay, then secondly we have to discuss about ABAB type. This is ABAB type arrangement. Here look at the first row. It is the simple one-dimensional arrangement of particles. There is no change in that. Then look at the second row. In the second row, what is the difference? Here the second row is somewhat inside. Okay, Mama. So in the ABAB type, the first row is arranged normally. Okay, it is a normal one-dimensional arrangement. Then when we place the second row, there is a little change we have to do. What it is means, here when we place the second row, the spheres of this second row are placed in the depression of the first row. What is called as depression? Look here, if we consider this as the first row arrangement, the depression in the sense the gap between the two atoms, that is called as depression. Okay, okay, since the arrangement is different, here we can name the first layer as A and the second layer is B. Now the third layer is similar to that of the first one, and so again third layer will be named as A. Then fourth layer will be similar to that of second layer, it will be named as B type, and so here it is called as ABAB type arrangement. Okay, so what is ABAB type arrangement? Here the second row spheres are arranged in such a way that they fit exactly in the depression of the first row. Okay, and the first row is denoted as A, whereas the second row will be denoted as B. Then third row is similar to that of first row, and so it is named as A, and fourth row is similar to that of second row, and it is named as B. Okay, and so this arrangement is called as ABAB type arrangement. Now let us calculate the coordination number. Okay, so what is called as coordination number? The number of neighboring particles per an atom is called as coordination number. Look here, if I take any atom, if I take this atom, okay, here it is surrounded by how many atoms? 1, 2, 3, 4, 5, 6. Okay, so here each atom is surrounded by 6 other atoms, and here the coordination number is 6. Okay, and this is more close than the previous one. When we compare this type of packing with AA type arrangement, it is the closest approach. Okay, and it is called as hexagonal close packing. The previous one is called as square close packing, whereas AB type is called as hexagonal close packing. Okay, so with this AB type is over. Okay, okay, then let us see. Students, we have completed about one dimensional arrangement and two dimensional arrangement. Then we have to see about the three dimensional arrangement of spheres, that is called as simple cubic arrangement. It is given that when A type arrangement is repeated in 3 dimension, the normal AA type is when repeated, we will get the simple cubic arrangement, and this is the picture which shows the arrangement of AA type in 3 dimension. Okay, we will have 3 layers, and it is called as 3 dimensional arrangement, and so this type is called as simple cubic arrangement. Okay, okay, and here all the spheres of different layers are perfectly aligned vertically and horizontally. Each sphere has vertically and horizontally aligned with the spheres of the other layer, and here the coordination number is 6, which means each atom is in contact with how many other atoms? 6 other atoms, and so here the coordination number is 6. Okay, students, so how do we get the simple cubic arrangement? When the one dimensional arrangement is repeated in 3 dimension, we will get the simple cubic arrangement. Here all the atoms or all the spheres of different layers are perfectly aligned vertically as well as horizontally, and here the coordination number is 6. Okay, then second 3 dimensional arrangement we are going to discuss is body centered cubic arrangement. Okay, this is body centered cubic arrangement. Now the first layer is one dimensional one. Okay, the spheres in the first layer are slightly separated, and the second layer is formed by arranging the spheres in the depressions between the spheres in layer A. Okay, my dear students, the layer A is normal one dimensional arrangement. Now the layer B, second layer, is arranged in such a way that the atoms of layer B exist in the depressions of the first layer, as we have seen in the case of AB type arrangement. In the case of body centered arrangement also, layer A is normal one. In the layer B, the atoms are arranged in the depressions, and again third layer is similar to that of the layer 1. Okay, okay, and this pattern, the AB pattern, is repeated throughout this arrangement of body centered cubic system, and here the coordination number is 8. Okay, okay, so with this the packing of different types is over. What are the types we have seen in this video? First type of packing is linear arrangement of constituent particles. Here the coordination number is 2. Then secondly, 2-dimensional packing. Here there are 2 types, AAA type and AB type. In the case of AAA type, the coordination number is 4, and it is called as square close packing. In the case of AB type, the coordination number is 6, and it is called as hexagonal close packing. Then 3-dimensional packing, we have 2 different types. One is simple cubic system. Here AAA type is repeated for 3 dimension, and the coordination number is 6. And in the case of body centered cubic system, the AB pattern is repeated in 3 dimension, and here the coordination number is 8. Okay, mama. Okay, so with this video ends. It's very important concept, so you can pay more attention and listen carefully. Thank you.